apply. Now this is a standard library, but you can create your own custom materials also by giving all these properties, material properties. Correct? We are doctors of mechanics, right? So we should know our materials as doctor knows his patients. Correct? So materials play a very important role. What is the elastic modulus, Poisson's ratio, mass density, and so on. Even you can provide inputs in terms of curves, like if the density changes with respect to temperature, right? Or specific heat changes with respect to temperature, correct? So there are various curves also which you can just import it if you are having the data, or you can type in, correct? So material play a very important role. It is the foremost thing on which your result depend on, correct? So last but not the least, the few simple steps like where my fixture would be, correct? Where it would be mounted on, for example, fixture is applied here, and the types of loads. If the force is coming, pressure, torque, or gravity, which is the load coming on each and every object on the earth. And finally, we can mesh it. Now, since this is an FEA, finite element analysis, so we usually discretize our model into number of elements, correct? We divide it into number of elements, and then finally the results are obtained after the processing. So in interest of time, I have pre-hand created the results, right? So as you can see, these are the two parts. I have applied the materials and restraints. That is nothing but the fixtures, correct? So it is applied at this top and bottom locations. Now just make sure that whenever we are performing any analysis, we need to simplify our model, right? Like my interest is to check which type of bracket is suitable, right? When I apply 2000 Newton of load on it, this is my problem statement. Whether I should go for 4 holes, 3 holes, right? Whether it should be single rib at the center, 2 ribs at the extreme end, right? We should first have the focus on what part we are having interest to check the results, right? So I have simplified my model. I have not taken into account the entire assembly. I have just simplified it and removed any unnecessary parts, correct? And as you can see, I have applied 2000 Newton of load at the top, and I will get the results. Like over here, these are few values of stress, correct? I'm getting 46.9 MPa of stress, maximum stress, which is coming over here, correct? And if I check what is my yield strength of, or over here you can check what is your strength of the material. I just change the unit. It is well within the criterias, correct? And the displacements what I am getting, also very important is to check the factor of safety. Factor of safety also plays very important role whenever we design, correct? So over here I am getting factor of safety as 3, correct? Now let me just switch it to single rib configuration with 4 holes. Same, but it is single rib. And with the same conditions of weight, material, you would be able to check the results, right? It is always not necessary to over design your product. Like in previous case, there were 2 ribs, right? And I was getting stress more than this, correct? And in this design, with the single rib itself, I am getting good results, correct? Also, the factor of safety plot can be checked over here. So likewise, what my intention is to showcase you now with the three pins if you are performing your analysis, correct? Again, the stress location might change, but it is not necessary that it would fail. Like, let me show you what is the maximum stress coming. So it is coming at this location right now, right? Maximum and minimum stress locations, correct? Also, we have this very interesting tool called Design Insight. So whenever you design the product, you would be able to know where your maximum loads are coming. So if I take my slider towards left, it will show me which region is taking the maximum load, correct? And how it is getting transferred to the rest areas, correct? So likewise, you can design your product. So which areas are taking more loads. And finally, for comparison, I have used two ribs and with four holes over here, correct? And you can have a look at the results. So quickly you can check multiple designs on any of your product, correct? And you can move ahead depending on the results, that which product is giving me maximum stress values, or are the stress values within my criteria of prescribed, and so on. So this was just very initial level of static analysis in which you can quickly check multiple designs and decide on which is the best design. So the setup was pretty simple. What we have seen, we have done just the linear static analysis by applying the weight which will be coming on this bracket and then check the results. But what if I want to do a parametric design? That is, I want to change the dimensions, change the material, also change the loads on the single bracket. Now, I am sure that with 2000 Newton of load, it can sustain. But what if I change the value to 5000, 10,000, whether it could withstand the load up to 50,000 or not, right? Whether the thickness of the rib, if I reduce it, correct? So these are various questions that might come in the mind, right? In order to create more optimized product. So we have this parametric design also. So let me just switch in that. So once your design is ready, after performing the first level of static analysis, what I have done, I will perform a simple design study, correct? In this there will be various what if questions coming in your mind. What if I change the load? So I have just inputted the values of load over here. What if I change the height of this bracket? What if I change the width of this bracket, right? So you can provide all these values in just tabular format, and with permutation and combination it will create scenarios, correct? With the load value of 10,000, height and width, correct? And in tabular format you will be able to get the results, right? So with this configuration of 1000 Newton, 4" of height and 5" of width, the weight will be calculated as well as the values of your results, correct? And dynamically the modeling is also done. No need to design that part again. So if I change the configuration over here, the model will be changed automatically, correct? So this will, in one shot you will get 8 scenarios run together, and from that you can finalize which is the best scenario suiting our needs, whether reducing thickness, is suitable or not, right? Whether it can take such amount of weight or not, right? So the product what you manufacture is intended for its end use, correct? Or it will reduce your time in prototyping and so on. So second part was very much interesting in this parametric design studies, right? So with different shape and size, the model will be ready for you, right? No need to again model it according to the thickness and dimensions, from which you can finalize which will be the best configuration or the set of thickness, material and size for the product. So this is just the video what I extracted out of various design studies what I got by changing the height, width and thickness as well as weight which is coming on this part. So automated, very important nowadays. Instead of creating 8 number of studies in one shot, you will get the results of 8 or tens of studies together, from which you can check which is the best design, which is having also less weight, correct? Also one more thing, you can specify the values over here, right? If you want to have your results to be less than certain displacement value, that is results should be less than 2 mm, for example, you should have your stress always less than your yield strength of material. So you can specify here those values also. So software will bifurcate accordingly, correct? Or else you can specify displacement between 3 to 4 mm so that the results of between 3 to 4 mm will be bifurcated for you and model will be ready accordingly, correct? Right? So improving your product quality, reducing the time to market and remain competitive, right? So if we talk about any brand in this world, take example of Simple Mobile. So there is competition is like hell nowadays. So to remain competitive, again, we need to reduce our cost, and to reduce our cost, we need to reduce our manufacturing cost. So with this design study tools and the tools what I have talked about would help in reducing your cost and remain competitive in the market. So these are a few applications where it is used. We have seen such optimized parts in our vehicle wheel or rim, correct? Where there are such slots made, right? Also in any electronic heat sink component, right? Where there are various circular pattern available. So by creating thermal study, how much circular fins are required to extract the heat away, you can check that. So mass optimization saves money without compromising the quality, correct? So without compromising your quality, you can save your create your part with competitiveness. Then moving ahead, we have this topology optimization. Now, topology optimization means shape optimization, correct? If you want to change the shape, like this is in just a few questions, like, is this too much bulky? Let's have an example of this simple bridge, correct? Can weight be reduced? So these are a few questions which comes in our mind. How much weight we can reduce? What if, will it fail if weight is reduced? I'm talking about the weight of this bridge or weight of any component. Will it collapse if it is reduced? So let me introduce you to this next generation technology called topology optimization. with the simple concept. I will just open the model. Okay. Yes. Now, this is a very simple rectangular beam, right? And in topology optimization, SolidWorks will decide, or the software will decide, what should be the shape, what should be the topology of the product when you provide the material and boundary condition like load and fixture. Correct? So SolidWorks will decide the optimized shape, the topology of the product. Like material, I have applied plain carbon, I have fixed these two ends. I am mimicking the position of bridge. Correct? So these extreme ends are fixed and force of 1000 Newton is applied. And you can specify how much weight you want to reduce. So depending on this percentage, right, software will make the necessary design changes on the product and it will give you the final result. Correct? So you can specify over here. So it will show the current mass and final mass after optimization is done. Correct? And finally, let me show the results. Yeah. So what it is showing me, I will just go over here. Yes. How much material can be removed, which is okay to remove, right? And this is the area you must keep in order to satisfy the need. Like I have applied 1000 kg at the top, right? To sustain that weight, this should be the design of your product. Correct? So with this slider, you will be able to check how much material you can reduce. Correct? Likewise, if I go on reducing the material, for example, from 30 kg to say, for example, 60 kg, 60 percentage, sorry. So it will give you good idea of how your design would change. What if I reduce it up to 90% by keeping all the boundary conditions and materials same? See the results. So it has even created a cutout from the within. Now we know that why bridges are having arc and why they are not bulky. Correct? So this will give you good idea about your product from where we can reduce the material and earn more profit on the part. Correct? And finally, what I have done, I have extracted this add geometry and I will create a analysis on this extracted geometry and I will run it to just be confirmed that what are the stresses coming on my product. See, the weight is applied from the top and bottoms are fixed and you will get the results. Correct? So this is my topology optimization. Software will itself decide what should be the correct shape of my product so that it will withstand the loading criteria. Correct? So this is just exaggeration of the results. 3000 times I have just exaggerated the results, or what is the displacement, which is very negligible in this case. Correct? So this was 30%, 50% mass reduction, 60%, 70, all the way to 90% mass reduction I have gone. So this was my design space. This was my initial design, right? Then after topology optimization, I got the model ready, right? And then I analyzed it to just be sure that it could take up the weight or not. correct? So this is a pretty good tool which is available. So now it is less bulky, the weight is reduced, and the design is also safe. Now you might understood the importance of mass reduction optimization, which we all hear somewhere day in and day out. Correct? Now we can see the results. The design is pretty much safe. Correct? Now these are few machines which we come across day in day out. Correct? Which are used for construction purposes. Now my next case study is on this. We all know this self-loading concrete mixture. Correct? You might have seen it. So it will take up the material and it will load it in this cylindrical concrete mixture. So the arm plays very important role, which actually helps to dig the material and pour it into the bucket. Correct? So these arms are very important, right? Because they're very vital role in taking up the load and pouring it into the circular bucket. So I have done this small case study about the impact analysis. So I have again simplified my model, correct? Instead of going on the entire vehicle, I have just taken the section of it where my arms are playing very important role. Like there will be one digging load when it will dig up the material, and second there will be one side load also, correct? It will be less in quantity, and finally there will be gravity load also, correct? So keeping in mind, I have decided this loading conditions on my model, and let me just check that in SolidWorks. Yes, I'll just go over here. Now this is my assembly. It is made up of various sub-assemblies, correct? This is my bucket. Then this is the fixture, right? And these are the arms, right? So the material will be filled in this bucket, then it will be raised, and then it will be poured into the drum, correct? So deciding the boundary conditions also play very important role. So in this case, I have also applied few connectors. So we have this option of applying any type of pin, bolt, connectors, means spot welding or edge welding and so on. So let me just open one for you. So we can see there are various holes, correct? So I have just applied a pin here, selected the material of the pin and the tensile strength data. What is the tensile stress area of the pin? So when pin is sheared, correct, how much area is coming, as well as the strength of pin, what is the yield of the pin, as well as safety factor, correct? So software will also let you know whether any pins are failing or not when such loading is done, correct? So the loads are applied at this top side and at the side load is applied if there are any side movements coming on the part, correct? And these are the few results. I have just created this animation which will give you a good idea of how the product would be behaving or in which direction the displacement is occurring. I have again exaggerated the results for you by 10 times. Just zoomed the correct. So these are few displacement results, stress results. From this you can identify where the maximum stress is coming, right? As in this case, if I showcase you, so displace, I will just go over here. So the maximum stress what I'm getting is 2000 MPa, which is at this bracket. If you look very closely, and in the rest area, it is pretty much within the yield limit. And yes, even these arms are having more stress, right? So we will come to know which parts to focus on, right? By changing the design of this bracket, by increasing the thickness, changing the material, right? Or by changing the thickness of this arm, right? It will help us to prevent the failure in any worst loading situation. Correct. Now, if I talk about this pins, what I have applied, whether they can take up the load or not, that is also very important question. So it will directly show you the results. Which pins need attention, where safety factor is less than 2, correct? And which pins are okay, where safety factor is more than 2, correct? So it will help you to decide what should be the material of the pin, what should be the diameter of the pin, right? Are pins sufficient to take up the load or not, and so on. Correct. So this was one example of this self-loading concrete mixture. So how to deal with such kind of applications. Correct. So we have seen this pins can also be analyzed to check whether they are failing or they are okay. This is just a small animation what I have extracted out from the results. Yes. Now we have seen the topology optimization in that previous case. It was a simple rectangular beam, right? But what if I want to optimize such kind of geometry? That arm I have taken, right? So how much weight can be reduced without hampering its intended purpose? I should not remove too much weight so that the part actually fails in the practical application, right? I should remove only some amount of weight so that its intended purpose is also not hampered. So let me move ahead. So for this arm, I have applied the weight of 7,000 Newton, which is coming over here, where and there are fixed hinges at the back side where it will move up and down, correct? And again, my goal was is to reduce the mass by 30%. Also, I need to be sure that FOS is greater than 1.25, right? So these are the few inputs what I have given to the software. So let me just open it. Yes, correct. Also, you can specify preserved regions. Means there are few holes where bearings might be coming or pins might be coming. So software should not remove material from there, right? So I have selected few regions, what you are seeing in this light blue highlighted color, where software will not remove any material from this region, correct? So you can specify this preserved regions also. And since it is symmetry, so I have applied a symmetry type of condition, right? And once your results are ready, so I was able to reduce the mass by about 20-22 kgs, correct? So it has beautifully created slots which run from top to bottom, correct? So the original weight was something 93 kg and optimized weight is 71 kg, correct? So let me come back over here and show you few more settings like mass reduction. Also what I specified, the factor of safety should be greater than 1.25. If I specify here that factor of safety should be greater than 2, so accordingly it will reduce the mass, correct? but I have specified it 1.25. So you can specify the values according to your need. And keeping in mind this values, it will show you the results. Correct? So it has created these beautiful ribs at the center from where the weight can be reduced, and then it can be used for your intended purpose. Like saving 20 kg in this single arm is pretty huge, right? Likewise, if you talk about more components in any assembly, it will save our material manufacturing cost, right? And other costs which are included. So this is very integrating next generation technology. So you can create smaller, lighter weight components, right? Also, if you want to 3D print any component, once your optimized part is ready, you can extract out the .stl or those files also, and it can be given to the 3D printing also, correct? Now, going ahead, lifespan of products. So this is a very interesting picture where we showcases us what is the life of any product, from piece of paper to degradable plastic bags, which is having life of about 10 to 20 years. Now, why I'm talking about this, right? Because to predict life of any product, we perform certain analysis, right? So we will perform fatigue analysis on this and check what is the life of the product or how much years it could withstand, correct? So many systems generate repeated or variable loading, right? So the products what you are designing in your company, in your startup, would be having rotating parts, vibrations, and so on, correct? So how to deal with that? So this is simple theory how the failure occurs, the crack initiation, crack growth, and finally it fails, right? So this is the pictures what I have taken from the practical testing. Now, one example which I would like to showcase you today is which crank will last longer, right? So there are various failures of crank. It can fail, but we need to be sure that the crank what we design, which is used in our regular bicycles, it should last for 10 years, 20 years, or how much years, correct? So how that is decided? So these are few design scenarios or failures of the crank. Now I did a few mathematics over here. The average cyclist makes 5 trips per week, so spending just under 2 hours on their bicycle and covering 25 kilometers. Per year, it is 1440 kilometer. And if I take the standard wheel diameter, so it moves 1.76 meters. So if we could design the crank to last 7 million cycles, right? So the cyclist can travel 1,23,015 kilometers in his lifetime, which could issue 8.5 years of warranty. So I did some reverse calculation, correct? And let us check which crank or which design which I would be doing is better, right? So it should satisfy certain criteria, that it should have 7 million cycles, right? And I'm having with me these three designs. Let me just jump on to the tool. Yes. Again, this is a sub-assembly consisting the part crank. There is this pedal and there are these sprockets. So I have created configurations here. This is my first design. Then this is my second design. And this is my third design. Correct? and I want to check by application of weight which design is suitable. Again, boundary conditions are pretty simple. I have just given here the fixed hinge type of boundary condition at all these holes, and force is applied of 1350 Newton, which is around about 130 kg. Now, whenever we perform any analysis, we do it for worst loading scenario. Correct? What if maximum load is applied on this pedal? And depending on that, I get to know what are the maximum stresses coming. Correct? So over here I'm getting 215, and the factor of safety I'm getting it 1.28. Correct? And if I talk about fatigue analysis, we provide fatigue data to the model whenever we perform any fatigue analysis because of constant loading and unloading. That is number of cycles versus the stress value. Right? As number of cycle increases, the stress value reduces. So we apply the fatigue data, and then software will show us where is the maximum damage occurring on the product. Right? So more than 100%, this area is failing, and what is the life. So where there is maximum damage, the life of product is minimum. So it could withstand just under 4 million cycles only. Right? Likewise, I have just copied the settings to this new model, and I have just run with the same boundary conditions. The weight is applied at this pedal, and I got this result. Similarly, the fatigue study is done for the same model, where results were pretty huge. From just under 4 million cycle, it went up to 13 million cycle by changing the design. Correct? Now, what if I change my design and create a bit curve over here? Right? Whether it could withstand or not. So that can be checked. So let me again jump onto the fatigue. Yes. So by providing few design change here, the number of cycles reduced to 1.3 million. Correct? So by providing small design changes, your life of the product change tremendously. Correct? So which is the better? The first thing what I did, I simplified my model. I removed the unnecessary parts. Correct? And with these three designs, I came to know that design 2 is the best design. So what my point over is here is, from various designs what you have in form of 3D models, you can check it and perform fatigue analysis, whether which product will give me maximum life. Correct? When it is put under its intended purpose. Second design proved to be good design for such kind of applications. Okay, so these were the few topics that I covered in the structural analysis, but what would be my next topic is the computational fluid dynamics, right? Where a fluid play a very important role. Either it can be liquid, gaseous, etc. Like an example of wall or an example of process industry. Correct? So today let me showcase you an application of electronic box. Correct? So let me just open the model. Yes. Let me just hide a few components so that we can check. Yes. Okay. So there is PCB laid over here. Then there are a few electronic components, right, which are generating heat. So my main intention of flow simulation is we need to check how much heat is being getting generated in this component, whether it is successfully extracted out from the vents, correct? And fans play very important role to extract away. So either my fans are capable of extracting away the heat from the system or not. correct? So these are the few things that I want to check. So let me again unhide it. So over here I'm having few configurations. Like this is solid lid. What if I create few slots here? Let me just hide it again so that we can check. Yes, correct. Or what if I create a different type of slots like this? Which is the best suitable configuration, which is helping me to extract away the heat properly from the system. Now, setting up the flow simulation study is also pretty easy as setting up the structural analysis. So this time I have just selected this flow simulation add-in, right? And your flow simulation tools will be activated here, correct? So creating study is again pretty simple. Nowadays, electronics play very important role in any machine. So we need to create a very compact electronic assemblies to reduce the size of our product, correct? So we just select the unit system. We decide whether flow is going to flow within the closed cavity or flow is going to occur outside the product or around the geometry, correct? And all the conditions like gravity, rotation, and so on can be specified here. So these are the type of fluids, that is gases or liquids, that can be used in my analysis, correct? And once you have created your wizard, you can apply material also. So let me just hide these components. Yes, great. Again, solid materials are applied to the respective parts, right? Some are made up of aluminum, some are made up of steel, some are made up of stainless steel, and so on. Next, environmental pressure is applied at these two openings, correct? They are connected directly to the environment. And fans are also created over here to extract the heat away from the system. So it takes care of each and every aspect, correct? So there are few AC and DC fans available inside the software, which are standard fans, right? So you can specify what is the volumetric flow rate of the fan. You can also give them in form of table, like what is the flow rate versus pressure difference, correct? So fans can be created to extract away the heat from the system. And few heat sources, correct? Which regions are generating how much heat? Like this internal component is generating 30 watt of heat, right? There are heat taking elements and heat dissipating elements. You can also apply two resistor components also, correct? In this electronic industry, two resistor components are used everywhere. Even PCBs are created over here. So there are these two PCBs what I have created. What is the thickness, how much layers, everything can be mapped here. How much number of conducting layers, what is the effective specific heat, specific density, everything can be mapped up here for that PCB. And finally, let me just show you the results once you have ran it. Sure. Yes. So it will help you to check which regions are generating how much temperatures, correct? Whether the temperature is more than the intended temperature, right? Whether there should be more fins or the cutout should be more, right? Like I have created here one cutout. Yes. correct? And finally, what I have done, I want to check what are the temperatures at different regions, like what is the average air temperature, what is the maximum air temperature coming, what are the temperatures at chips, what is the temperature at PCB boards. So everything can be listed out here, right? So directly you can also clone your studies to the configurations that you have created, right? So automatically all the settings will be reflected to another configuration. No need to do the entire setup again. If you want to do the analysis with the slotted lids at the top, it will again show you the results for that, right? So depending on this, you can verify how much slots are required or how much fans are required so that heat is extracted away very smoothly, correct? So this was very interesting example of this electronic box, right? Designing of this sheet metal electronic box is very important because we need to be sure all the electronic components are also mounted inside this casing, as well as heat is dissipated correctly away from this box, right? Similarly, you can perform analysis of such examples of pump, blowers, and so on. But today I am interested to show you one external analysis on this solar structure. Correct? We all are aware of the solar structures which is mounted. I'm talking about industrial solar structures, not the one which are mounted on our household solar structures. Correct? So the physical conditions are like the fluid is air and it flows at 47 meters per second. Right? So it should withstand any uh, cyclonic conditions as well if they might come. Correct? So over here, this is a simple model and I have created few weldments over here, right, for solar structure, and panels are mounted on the top, correct? And settings are pretty much easy. The air will be coming at 42 meters per second from this back end, and I want to check how much pressure is getting built up at this back ends of all the panels. It should not lift away, right, as the wind passes through it. So these are the velocity plots. What is the velocity coming at each and every region, or what are the pressures coming, the distribution of pressures, correct? Also I have created surface plots at this back end of this panels, how much pressure is coming at this back end because of the wind which is flowing, correct? And you can also check the flow trajectories, like this, how the actual flow will be occurring on your product. You can check that too, right? And what is the outcome, right? So the results what I got over here were how much pressure is getting built up at this back end of all the 32 panels what I have applied here at the back end. So I'm getting 1,15,500 Newton of pressure getting built up at this back end of the panel, correct? And this pressure can be used to perform your static level of analysis, right? So what I have done, and yes, of course, you can perform transient analysis also, like this, correct? Okay. Now, once I have got the result of what is the pressure coming at the back end, which was something 1,15,000 Newton, I will do the structural analysis to check the rigidity of the structure. So the materials are applied and the pressure values you can apply at the back end of the panel, and you will get whether it can withstand such speed of velocity of air or not. So this is my displacement plot of the structure. Correct? Also, few more studies that you can perform are like solar excess studies. If you want to check how much whether your assembly is getting access to the solar or not, we have this interesting tool called solar access studies, right? So in a day you can select the month, day, and the location where this will be mounted, and then it will let you know how much shade is going to fall on your solar structures so that it can generate maximum energy from the solar. Correct? These are the few capabilities. This is like mixing air inside the fluid, right? If you want to mix fluid with the fluid, right? This is an example of vibration. Whenever vibrations are coming inside the tank, how your fluid would be behaving. So such kind of analysis can also be done. And few applications in aerospace or automotive, consumer products, and few applications in energy process and power industries as well. Now, lastly, let me come back to the topic about the plastics, right? Now, the mass use of plastic started in 50s and has steadily grown ever since. Today, more than 300 million tons of plastics are produced annually. The popularity is not due to its low production, but also its numerous characteristics like low weight, acid resistance, and flexibility, right? In addition, its flexible properties, it has many much examples or applications not only in medical, building, technology, aircraft, and automotive, right? But also, if we look around, there are plastic parts everywhere. A basic injection molding overview, we all know there is sprue, runner, and a gate system. And finally, the plastic is filled inside the cavity to form the net shape. So this is just the basic overview of the plastics. Advantages, complex geometry can be done, right? High volume, thousands and to millions of parts are manufactured per year. Cycle time is less, within 3 to 30 seconds parts are produced. Low cost per part. Detailed features and complex geometry can be produced and chemically resistant, right? And they are light in weight. The simple setup. So before we jump onto into the plastic, so just a brush up that plastics go in here, melt here. This is where the mold goes, and plastic part comes out. A very basic uh, overview of the injection molding machine, right? So these are the reasons, as I have uh, explained you, why plastics are really helpful, and also they are visually aesthetic in nature too. Now there are few defects which might come like warpage. If you have designed your product which consists of any plastic part, then they might undergo warpage or air traps. There may be sink marks also. There may be weld lines. There may be short also. The cavity may not get completely filled, etc. So there are various unanswered questions. Is it manufacturer? Is it manufacturable? Whether quality would be good, right? Whether there would be any air traps and so on. So how to address these issues? So with the help of this plastic tool, I will just showcase you. You can address many manufacturing defects. Correct? So let me just jump on. Yes. Now this is a very small example of smoke alarm. So this is just a configuration what I've created, and it is having various components inside it. So let me just open one single part. Likewise, we have seen simulation, we have seen flow simulation. The third is the plastics. So all your plastic tools will be popped up here, correct? Yes, right? So first thing, what we do, we provide the material for the plastic, right? Either it can be user defined or we have the default database also. You can sort it by family or sort it by company, right? If you're using plastic of this buyer company, so all these standard materials of plastics are included, correct? Then you can specify various settings over here. What should be the fill time, right? What is the injection pressure limit, and so on. And once you run it, you will have an idea whether the plastic would get filled in your cavity, whether there would be any shots like over here. The plastic is not getting completely filled inside my cavity, correct? So if you look closely, uh, you can change the thickness if required, and then check the results, correct? So various plastic defects can be eradicated virtually with this help of SolidWorks plastic tools. Let me just play. Yes. So this is how the molten plastic would be entering the gate location what I've specified here, correct? And various results like air traps if they are occurring, then what is the pressure at the end of fill, are there any sink marks, right? Number of results can be checked. Even you can perform multiple mold cavities, like a family mold is created with top and bottom casing both together. If I want to extract out, that thing also can be done. So you can create the model accordingly and then check for the results. But after giving all the boundary conditions, here it is. So you can design your virtual runner system also, runner system gate design, and so on, correct? And then you can even perform runner balancing so that all the cavities are getting filled at the same time, or one cavity may fill before another cavity. Those errors also might occur, correct? So with this plastics, you can simulate to design better plastic parts, correct? Now I have just showcased you regarding to this our conventional desktop products what are available inside SolidWorks with respect to analysis. Now let me introduce you to this 3D experience platform, correct? Which is a cloud-based platform. Now the biggest challenge to leaving the engineers at home is reduction of collaboration, right? Because of this COVID area, most of the engineers are working from home or from remote locations. Now it has become a virtual shift. Most of
Hello.
them, hello, yes,
Yes, Gaurav bhai.
yes,
Uh, uh, I would like to tell that we are having 10 minutes only for
yeah,
this session.
yeah, sure.
So,
I would be just giving the introduction. I am not going in detail,
okay,
just in last 10 minutes, and then we can open for question answers.
okay. Thank you.
Correct? Yeah,
Thank you.
welcome. Yeah. So remote work, collaboration, and virtual shift, right? So as I have mentioned, most of the companies are providing work from home to their engineers, correct? So over the last 1 year or so, the majority of us have had to adapt to this new normal, right? So without the right tools, this working environment can present some real challenges when trying to continue designing, right? So some companies may opt for VPN networks, but again, there may be issue with that. It may get stuck, or else they can go to the generic cloud storage where they can store their data over cloud like Dropbox or Google Drive. But again, there are issues, right? Or laptop hard drive or emails. But with this next technology shift in this 3D experience platform, so it is announced by Dassault System to be cloud-based collaborative platform for all size and business. So it includes different domains like design engineering, governance, simulation, and manufacturing. Correct? So it deals with all the domains. Correct? And it is having all the information at one location. So you will just have to log in over your any browser with your credentials, and you will be able to design your product, even do analysis over to the cloud. Even you can create communities, share your files within the communities, and so on. And in that, if I talk about simulation part, right, one of the domain is simulation, right? So from simple SolidWorks simulation to this high end simulation, we have created a cloud based platform, right? Which you can perform complex physics, not only implicit but explicit analysis also. This is an example of small dental implant, what I have done, which is used by dentists, correct? So they apply the weight on this crown and to check the rigidity of the screw, whether it is taking up the load or not, correct? So this is my user interface of this cloud simulation tool where you can check the results. Same goes with high end explicit dynamic analysis, like if you want to do crush analysis of any model, like crushing an aluminum tube. So this is my practical testing, and this is my analysis what I did in my analysis Simulia tool, correct? So these are the few capabilities what I'm showcasing. Same goes with this crushing of aluminum can, correct? So the same I did in my analysis, and the results were pretty good. And if you want to perform high level of contacts, where contacts play very important role, such an example of buckle. So these are the few applications if you want to perform frequency analysis of engine, correct? Different mode shapes can be extracted out, drop test, vibration analysis, impact analysis, bullet impact analysis, and so on. This is my 3-point bending analysis. So these are the few capabilities of Simulia, right? And major advantage is it is cloud based. So no need of any major IT overheads are required. And lastly, we are having the same fluid dynamics also over to the cloud, which covers broad physics, steady state to transient, laminar, turbulent, and so on, right? And there is an interdependability between SolidWorks and your cloud platform. So you can model it in SolidWorks and export it to the cloud platform and then run the analysis to check the results. And finally, I like to summarize that these are the analysis tools which you can leverage for your new product and development, starting from your desktop SolidWorks portfolio to high-end cloud simulation portfolio, which is 3D experience. So if I talk about the key takeaways, so it is designer-centric user interface, it is on cloud, integrated to the CAD, right? Across all skill levels, whether it is new user or experienced FE analysis can make use of it. And collaboration is the key. You can collaborate with anyone, anytime. Even you can uh, work on any browser, right? Now the setup is pretty simple for this new cloud-based technology. So you install your client on computer, it is connected to the cloud, right? And you can even use it on your mobile phones or desktop, right? So thank you for having me here to present you in front of you this new analysis tools. So you can ask any questions if you have. So I am open for the question answering session.
Yes, if anyone has the question.
So next, I would like to hand over Mr. Hiren for conclusion parts, and then we can have the question answering sessions once the Mr. Hiren just concludes his session. I'll just hand it over to Mr. Hiren.
Yes, yes,
Yeah,
please.
yeah. Uh,
You can stop sharing the screen.
yes, I will just stop sharing.